I am going to discuss about work and energy for rigid bodies. Now, we have discussed about kinetic energy, that is half mv square, and we also discussed the work and energy principle. Work and energy, that means work done on the particle by the external forces increases the kinetic energy equal to the amount of the work only. So, kinetic energy of a rigid body is the sum of kinetic energies of all the particles comprising the rigid body. A rigid body consists of so many particles. We can consider that a rigid body consists of infinite number of particles, but that does not matter, that each particle is of mass then tending to 0, and therefore, we will have some kinetic energy. Instead of summation we have to do integration, but actually the definition is that kinetic energy of rigid body is the sum of kinetic energies of all the particles comprising the rigid body. In the continuous system, in a integration is basically summation. Now, we consider three cases of motion. One is the translation. You know that in the translation, each line in the body moves parallel to itself. So, there is no rotation, omega is 0. So, the translating rigid body has a mass m, total mass may be m, and all of its particles have a common velocity v. Then the kinetic energy of any particle of mass mi of the body is Ti is equal to half mi v square. That is the. So, for the entire body we have Ti is equal to sigma half mi v square, and you can take that this common. So, it becomes half v square into this sigma mi, and sigma mi is the summation of that becomes the total mass m. So, therefore, kinetic energy then becomes equal to half mv square. That means, kinetic, this expression is similar to that expression for a particle. So, instead of particle mass, now I am putting the mass of the whole body, and therefore, T is equal to half mv square. So, this is in translation, we do not have to worry, but still we talk about the velocity of the mass center. We say body is moving in the translatory motion. What is the velocity of the mass center? Other velocity of mass center should be same. So, like this, that here velocity of the mass center g is like this, and velocity of any other particle is also same. So, Vi is equal to V. This is true for both rectilinear and curvilinear translation. No matter body is moving in a straight line or body is moving in a curved path, you have got the same type of relation. So, there is no problem in this, that you can. Now, about the when the body is only rotating, that you know in this case. Now, let us discuss the second case, that is rotation. Body may be rotating about an axis. In that case, for a particular that particle, you have got the velocity, that is omega times Ri, where Ri may be the distance from the fixed point. Suppose this is the body, and this body is rotating about this point. So, therefore, what happens, that I will say that its velocity is omega times Ri. So, omega Ri, so that you have to, so velocity square is omega square Ri. Omega square is common for all the particles, so it can be taken outside. So, for the entire body you still have the expression T is equal to half omega square sigma mi r square, and that is equal to half I0 omega square, where I0 is the mass moment of inertia of the body about the fixed point O. This is the fixed point, so it is about. So, therefore, if the body is rotating about a fixed point, we know a fixed point about which the body is rotating, then T is equal to basically half I0 omega square. Okay. It may be rotating about that fixed point, and or it may be some instantaneous center of rotation, then also we can find out half I0 omega square. Here you have to find out the mass moment of inertia about the fixed point. Now, we discuss the third case, that is general plane motion. Now, we know that there is a theorem of Chazal that motion of a body in a plane can be decomposed into the rotation part and translation part. So, let the velocity of mass center g is v and its angular velocity is omega. So, now this type of situation is there. See this body, it is rotating, and at the same time the mass center g is going with a velocity of v bar, it has been indicated. So, any particle on the body, let us say this, that is at a distance of r I, and this is inclined. Okay. Now, this is at a distance of r I. Now, this is having a relative velocity with respect to g in the perpendicular direction, because to r I, because in the rigid body the particles do not move towards each other. So, they cannot have any velocity component towards any other particle. Two particles cannot have relative motion towards their line of joining, and therefore, the relative velocity has to be in this direction, and that is r I omega. Now, let us say that this velocity, we have shown that this velocity as a horizontal for our convenience. This does not affect that our general treatment. So, therefore, what happens that here you have v bar, this is the thing, and r I omega, and if they are making an angle theta, then we have resultant, that resultant velocity is v I, that has been obtained by parallelogram law of addition of two vectors. So, the vector has, so you know that this velocity is represented by one side of the parallelogram and this is represented by the other side, and the resultant is coming like this. So, this is the expression you have got, and then now we get v I square by parallelogram law, we only get v I square is equal to v square plus r I square omega square and plus 2v r I omega into cos theta, where cos theta is what? Cos theta is the angle between v bar and r I omega. V bar is considered horizontal. So, therefore, if we draw and if we consider that as a x axis, and let us say this was a y axis vertical. So, r I makes theta with this thing y I. So, therefore, that has been indicated in the figure, and therefore, this is for one particle. So, for one particle the energy will be that if we say that the mass of that particle is m I, and we can do summation instead of integration sign. Now, I am just using summation, continuous system, it will convert to summation integration. So, that is half m I v I square, and like that you have to sum. So, this is sigma half m I v bar square plus r I square omega square plus 2 v bar r I omega cos theta, these things. So, let us discuss various terms here. Now, the third term in this one is r I omega cos theta, and if we see this figure, then we see r I cos theta becomes equal to y I. This is r I cos theta, that is becoming equal to y I. So, in this case, the third term is omega into v bar sigma m I r I cos theta, that means omega v bar sigma m I y I, that is equal to 0, because since basically sigma mi yi bar will be mass times y bar, where y bar is the y coordinate of the center of mass. So, that is equal to 0 because G itself is the mass center. So, in this figure that you have to see that this, if we take the yi times that mass and then sum, so it will be coming 0. So, this is the thing. So, this is now therefore, now here in the first term half mi v bar square. So, v bar is common now because it is the velocity of the mass center. So, it can be taken outside, and omega is also common, it can be taken outside. So, you get kinetic energy of the body as kinetic energy is equal to half v bar square, this is sigma mi plus half omega square sigma mi r square, and this is half m v bar square plus this is sigma mi r square half ig omega square. So, this is mv square and this is the thing. So, because I am taking r is the distance in this figure from the mass center. So, therefore, naturally ri, that means this is ri is the distance from the mass center. So, this becomes half ig, this becomes ig. So, half ig omega square, and this is, so we have got a nice expression for the kinetic energy of the body, that is half mv square plus half ig omega square. So, translational kinetic energy and rotational kinetic energy. Rotational kinetic energy is half ig omega square, translational kinetic energy is half mv square, and kinetic energy is the that basically capacity to do work because of its motion. So, both the things can be there. Now, we discuss about the potential energy. Now, suppose a body is moving in a gravitational field, then the work done by the gravity on the body is equal to minus delta Vg, we know. That means, when the gravity does some work on the body, then body's potential energy decreases basically. But if the work is done against the gravity, then body's potential energy increases because that work is stored there as this one potential energy. Now, so therefore, if a body is moving in a gravitational field, then the work done by the gravity on the body is equal to minus delta Vg, where delta Vg is the change in the potential energy of the body. Similarly, if the body is moving against a spring force, the work done by the spring on the body is minus delta Ve, that is where delta Ve is the change in the potential energy of the spring. So, these are the conservative forces. Generally, these forces we can be expressed by, so work done by these forces can be expressed by potential. Now, if W12 is the work done by the forces other than gravity and spring forces, other than these conservative forces during the motion of the body from configuration 1 to 2, any 2 configuration, body may be here, that is configuration 1, it may move here, that I will call configuration 2, same body in a different orientation or different place, the following relation will hold good. So, total work done actually on the body is basically W12, because that is the work done by some other forces, and this is the work done by the gravity forces minus delta Vg, where delta Vg is the increase in the potential energy due to gravity, and here minus delta Ve. Delta V is the increase in the potential energy due to spring, that is equal to delta T, or W12 is equal to delta T plus delta Vg plus delta Ve. So, what we see from this? Delta T is basically increase in the kinetic energy. This we had obtained just by, we had Newton's law only, from that we derived this in the previous lecture, that work done is equal to increase in this one, and in this case W12 is equal to delta T plus delta Vg delta Ve. So, delta T is the increase in the kinetic energy, This equation is called work energy equation. It states that if the forces are conservative, the work done by the forces other than gravity and spring forces which have been accounted for in writing potential energy will equal to change in kinetic energy plus change in potential energy. In this this delta Vg, delta Ve are conservative, and even if that this other force is basically will cause, if we consider even the non-conservative force, then also this relation remains valid, because delta T, because this directly comes from Newton's law, but you have to recognize that are the forces properly. Now, this is then we come to the virtual work principle. We have studied that in the statics, and here also the same type of virtual work principle can be used. The work done by the forces for an arbitrary assumed small and kinematically consistent displacement is called virtual work and is denoted by delta omega. So, work done by the forces, you know that you, so here you pay attention to each and every line of this work done by the forces. Body may be subjected to the forces are there, and we assume that, so there are number of forces are the, and we assume arbitrarily small displacement. You give that actually it is not the real displacement. Real displacement will change the forces, but this displacement is so small that it does not change the forces. Force situation remains same and kinematically consistent. Kinematic conditions are not changed. Actually, that means whatever that boundary conditions on the velocity and other things, if there is are two linkages, whatever that in the linkages between two linkages, the relations of the velocities remain same, then that is called kinematically consistent, and this work is called virtual work and is denoted by delta W. Now, if we use the work energy relation, so delta W will be equal to delta T plus delta V, that is the thing. So, therefore, here now delta T is basically delta sigma half mi Vi bar square plus sigma half I bar omega square is equal to sigma mi Vi delta Vi plus sigma I omega I delta omega I. This is omega I like that, and this is, there may be number of linkages, for that it is now mi Vi dvi is basically mi ai dsi, because we know that we have a relation V dV is equal to A ds, because A is equal to V times dV by ds, that relation is there. So, we make use of that relation, and you say that for a part, you know, this particle you get where because this is a simple kinematic relation, Si is the displacement of the particle and Ai is the acceleration. Similarly, I omega I d omega I can be written as I alpha I d theta I, where this is the alpha I is the angular acceleration. Consequently, we get delta T is equal to sigma mi ai delta si plus sigma I alpha I delta theta I. Now, mi ai is basically Ri on that, and this is delta si, and I alpha I is basically mg and delta theta I, for that mgi maybe we can say. So, delta W comes out to be sigma mi ai delta si plus sigma igi, this is I with respect to g, okay, this is subscript gi, and alpha I delta theta I, plus if we consider that MIG delta HI, virtual change in the height, and sigma Kj xj delta xj. K is the spring constant, xj is the displacement, and like that. Similarly, so this can be written as, so this expression has been written now. So this is the expression for the virtual work. So by this we can do. Now we will try to solve one problem by virtual work principle. Now consider that at this is the problem. There are two rods here, this one of length b, and they are moving on these are rollers which is moving on a rail, and this is theta, and this is b, and this is this one. So then what happens? Now this will be at certain time two identical rods of length b have been arranged as shown in the figure. The rods are allowed to move in the vertical plane due to influence of gravity. Now find out the acceleration of the rod at the instant depicted. So it is this thing here that you have to find out the rod, and this is now the kinetic energy T is equal to 2 into half, and we take that here this point is the point of zero velocity, because this is instantaneous center. So here instantaneously the velocity is 0. So about this we can say that it is rotating about this fixed point. So the kinetic energy is half I omega square, but two rods are there, so 2 times half, and about that fixed point it is 1/3 mv square. About its mass center, its moment of inertia is 1/12 mv square, but about the fixed point it will be half mv square, because this is the rod and this is about the mass center, it is 1/12 mv square, and this distance is b by 2. So this will be mass times b by 2, b square by 4. So you get 1/3 mv square theta dot square, that gives you 1/3 mv square theta dot square, and the potential energy is given by V is equal to 2 times mv2. If we take this as a datum and say that this is the zero potential energy, this line, then the potential energy of the rods will be negative because mass is below that thing. So this is, we will put a minus term here, minus 2 mv by 2 sin theta g, because theta is this angle. So it becomes mv times sin theta into g. So you get minus mv sin theta. Now when the rods are collapsing due to own weight, then no work is done by external forces other than the gravity forces. Hence T plus B should remain constant, and therefore delta T plus delta U is equal to 0. That means 1/3 mv square 2 theta dot delta theta dot minus mvg cos theta delta theta equal to 0, or 1/3 mv square 2 theta dot delta theta dot is equal to mvg cos theta delta theta. Then we get delta theta dot is equal to 3 mgb cos theta divided by 2 mv square theta dot delta theta, that is 3g cos theta divided by 2b theta dot delta theta. If you divide both sides by delta t, then alpha is equal to 3g cos theta divided by 2b. We get like this, and this is the answer of this one. Then if we have interconnected body, so for a system of interconnected rigid bodies, we can write 1 to 2 FDRC, and this is half mi Vc1 Vc1 square, and this is half mi Vc square. The force F includes not only the external forces, because internal forces they do equal and opposite work, they contribute to no work basically. So like we give this example that two bodies are connected in this case. So, this is the problem. Two bodies of weight W1 and W2 have been connected by a string. This one, this you can read, and then this one it is being pulled here and there is a friction force also acting. So, the work done by the external forces including friction, but excluding gravity force, is minus Fs1 plus P minus F2 minus W2 sin theta into S. This work will increase the kinetic energy of the system. So, increase in the kinetic energy will be this is W1 by 2g V square plus W2g V square again and minus W1 by 2g U square. So, therefore, this becomes W1 plus W2 by 2g V square minus U square. Hence, this work done is equal to this one. So, from this we can find out the final velocity given us the initial velocity u.